only 20 minutes long.
What?
It's only 20 minutes. Their presentation.
Oh, I thought it was 12. I thought
The whole thing's 20.
wow, 20 minutes is like forever.
How cool is this? How cool is this to be in the back of the classroom where your son is presenting and it's
We were down at, what is it, Pimento Hall. They were just giving some, for the last hour.
oh, you got to see some?
We had to watch them. They got there like 10. They were going off on like antimatter and matter.
Ah, cool.
Their relationship with neutrinos and stuff.
Wow.
Pretty neat.
Yeah, it's awesome.
Every single person who had a computer had a Mac.
Yeah.
Yeah, they were big in the Macs here.
Yeah.
I did notice that.
Like 6 people had these in their laps.
Yeah.
Yes.
Yeah, we parked on Dwight, about 6 blocks away. Just walked
in.
in.
Anywhere in the world to drive is easy.
Mom drove. She was a little hectic, but it was good.
Oh, no, I'm not trying. I'm here to talk. That's just my name's Derek Fraser. You are?
Joe,
Romo?
Joe, the guy just came in. That you're looking for just came in, and he left. No, somebody that you're looking for just came in.
Okay.
Yeah, and he left.
So, going to
Yeah, we're going to do it.
so we need this thing?
Yeah.
Don't seem to have a UES.
I have a connection.
Well, you one of these little adapters.
Oh, yeah.
Doesn't seem to have USB.
You know, that's not what he needs. He needs a video adapter, which he probably has. That's the guy. Right there.
Okay.
The other thing, this table,
Yeah, but then probably this is too far.
or to put that here so you can get it up a little higher.
The height is fine.
There's this guy too, so
Yeah, this should be.
I can keep running around.
Okay, very fast.
Yeah. Squeeze your fingers.
Yeah. I'm just going to kind of explain the slides. What we're doing is pretty introductory, but as a first project,
That's awesome.
I
Yeah.
think it went really well. And
Great.
It was really exciting and really understandable.
Right.
So
Cool.
I was really that really gets me excited about physics. Makes me want to
Right.
do it. I mean, when you understand something, when you're good at something, you're good. When you're good at something, everyone wants to do it.
Right.
The challenge is always good too, but you have to start somewhere. Get your foot in the door somewhere. So
Right.
Our perfect opportunity to open the door.
Yeah, it's awesome. Yeah, it's great.
Our feedback, we're interested in taking it one step further. And,
Right. Are you graduating this year?
No, I'm senior stuff.
Oh, okay.
Oh,
okay.
Year.
Oh, cool.
I think it takes another 2 years to graduate.
Yeah.
It's pretty tough. It's
Pretty normal, yeah.
But it's fun. It's good. It's going to take a little while, but it takes about 5 years. But I'm not in any hurry. I've got the rest of my life, and I figure that this is a good place to be in my life right now. So I like it.
Yeah, it's awesome.
Where are you from, David?
I'm from Miami. So I'm an hour from LA, north of San Diego, right there on the coast.
Oh, okay.
Yeah, what your accent was.
You have a good accent?
You have something.
Yeah, I'm sure. I mean, if you can pick it up, yeah, I think everyone has an accent. I agree with you on that. I think a lot of people have accents.
Start your.
We put this in the wrong place.
Okay,
Which one is it?
Perfect. That's awesome. That's awesome.
Oh, everyone's coming, huh?
Fellow colleagues, friends, sports.
Tom, these are my parents, actually.
No, I just met him.
Okay.
Yeah, we talked all about this now.
Okay.
Very excited.
And I don't want to show the speaker too much, because we have to keep pretty well to our schedule since there's all these parallel sessions at each time. So, having said that, and get started. The way we will do this is allow 18 minutes for the talk, there's a 2-minute warning if the person is not yet finished, and then we'll have questions at the end. If we don't use up all the time for a talk, we will have more time for questions because to not get off the stage starting another group. So our first speaker is Darren Frazier. There you are, okay. Cal-Poly, it says Cal-Poly Physics, is that Cal-Poly Pomona or?
San Luis.
That's the one.
Does it say it on there?
No, it doesn't. Attenuation of visible electromagnetic spectrum, deals.
Alright, well, hi, my name is Doug Rowan. We're basically doing a project for the summer. We're doing some research on the attenuation of the visible electromagnetic spectrum, which is basically how light dims the ocean surface and at depths of down. Advisor was Tom Bensky, Dr. Tom Bensky. He's a professor at Cal-Poly. We're 2 students. We're third years at college. Our basic outline for this talk is basically going to at the location of research where we did all our research and experimentation, the questions that we asked, how we tried to solve these, and how that leads to future work. So getting right into it, our location where we did our experiments was at a pier about 10 minutes away from Cal, right Bay. It's the old Unical Cal-Poly Marine Science and pier that was donated to us. So the benefits of using the pier was that it's half-mile out into the ocean, and there's 30 of water at the depth out there, so we can drive out on this pier all the way out to the end, and the water is unobstructed, just ocean water. So we can basically use the water with experiments and have the same place of experimentation every day for weeks on end.
To our phenomenal question, what are we studying? Why are we out there here? Well, we want to know what happens to light when it's we already know that how debris, you know, when a storm comes by or whatever. How does the attenuation of light in the ocean in those different settings change? Does it change? How does, you know, do all the wavelengths that attenuate, they all attenuate the same? Or do some of them fall out first and are others able to make it down? These are some of the questions we had, and we wanted to find answers for these. So we decided to, since we had these questions, we needed to figure out, okay, how are we going to answer these questions? Well, first idea, you know, in the beginning, we said, hey, let's use a photo. So we decided to use a photodiode. This here is a picture of our first apparatus. I'm sure you guys are all probably familiar with photodiode. Photodiode would only measure density, so we're not answering all of our questions. We couldn't get to the wavelengths. But anyway, so we started out with the photodiode, we built this apparatus. We had problems, you know, with trying to get making the PVC pipe watertight.
It's definitely a homemade experiment.
Right, in the beginning, right, we had a lot of problems with getting PVC pipes. Then, you know, with photodiode, it puts the light shines down, giving the voltage, right? We can get a current. That current you can op-amp circuit, which you know is delicate, so very, very sensitive. The problem is that the individual wavelength, so it's not really working for us. So you learn things as you do an experiment like this. Time lag was another important data, and that's not great. You know, we're not getting exact. So, despite all these problems, of our first, we did get this curve at the top of it kind of, this is the ocean, and right? The intensity of we do not do this. In the first view, ocean, seeing the light.
We're basically not integration.
And we believe that, Joe. We believe that too.
It's a nice type of curve here.
Right, and that's one of the. Hey, look, it's not linear. Definitely a curve y equals to the negative b, where b is constant.
So, from working with problems, we identified our task of finding. So, what we came up with is a fiber optic cable, connected to connected to a computer. Procedure of way computer program that would, like as an example, sorry, we would have is this would be the wavelength. So okay, the 500, 700 nanometers, that really complex. That's kind of what it looks like, and then drop off. So in terms of going back here, this basically lower the surface, and then the rope is marked with half-meter increments of time, and there would basically, and it would accrue.
Think that we get a graph.
So basically all method, we're getting real time data, time on the computer screen.
We can see the intensity of each individual wavelengths. Now we're getting a question. So this design, we do still have problems when we're trying to iron those out, but for the most part, I think what this actually be when this would be right before the ocean, place right above the surface, reading, sunlight, and these are all the wavelengths. These are all the wavelengths within white light. You'll notice from 0 to like say maybe 75 to 800 nanometers spectrometer. So
It's only accurate.
Those are special equipment. So
compiling the different runs, the different looking picture, oceans, and then every half inch from depth, it draws. So if we can take a slice at say 600 or 100 and a little exponential.
B, where B is our coefficient. So this is what we're, coefficient B is take them at every 2 minutes. So can you back the graph real quick? So if you took a slice each one of these into 2 nanometers, you get that was right. You slice them like this, you get a curve that was with that we took the we indexed out when we attenuation coefficients. So these attenuation coefficients. Why is this? Why? Well, and that's a relationship. I'm sure it's really the believability of our data. So within these that about 450 to about our data is pretty believable. I mean those curves
are very accurate.
So we took the one out here. I'm not really quite sure. This is what we got. Attenuated. As explained.
of our and
Yeah, we gave us, you shoulder.
after averaging base squats and then like might be hard. Okay.
The natural laws come out of it. Okay. We'll skip these. If I can only get this computer working. I push the on button, it don't go. On the internet, it's called Atom in a Box. And in it, you have all the wave functions of the electron around the hydrogen atom. The first excited state looks exactly like what I've shown you, the in wave and the out wave. And then you can look at all the different excited states. And all you have to do is look at that atom in a box from UCLA, Dean Dowder, and you reinterpret your mind to say that the wave function is the electron and there is no particle running around inside. Done.
Any idea what generates the wave?
Huh?
Any idea what generates the wave?
It's a property of the wave medium. The wave medium which is established by all the matter of the universe, according to Mach.
How do you compute the mass of the electron?
Huh?
How do you compute the mass of the electron with respect to West mass?
Well, mass is the frequency of
Yeah, but how do you get the number? I can get the number, so.
the frequency. Well,
How do you get 1/2 MeV?
you have any medium, like a stretched string, right? You twang it. The frequency of that string, or the frequency of a drum head, is determined by the medium. So, given a medium, you can determine the frequency. Frequency, of course, is mass. HF equals mc squared.
Yeah, I have no trouble with the concept of the mass, the particle as universe, with basically waves. But I do have a problem with the notion of the in wave coming into the center and somehow causing a rotation. I mean, what kind of a line group is that, or what symmetry group does it fall into that creates that?
Well, as I told you, I'm not mathematically very smart, but in my paper, I referenced the guy who did it. It appeared in the Journal of Theoretical Physics. Very highly respected. Also, Wheeler, in gravitation, has a lot to say about it. You want me to quit, right?
No, you got a couple more minutes, I'm sorry. No, I've been sitting all afternoon.
So I can go?
No, but we have, no, we.
If I can only get this thing on air,
No, it's not gonna happen.
Never got
that's
it.
not gonna happen. is it?
Yeah.
If this guy can't do it,
Let's see, there have been several attempts to try to describe the structure of an electron in terms of a finite structure instead of a point object, and those have been unsuccessful so far for several reasons. One is there's no clear reason why an electron of finite size would hold itself together. Why wouldn't it explode because of the electric charge, or how would it hold together? Another is with the electron spin, such that it is a finite size electron spinning would have to spin faster than the speed of light in order to have the proper electron spin. And another reason is the experimental upper limit for the size of an electron has been found to be about, right now, about 10 to the minus 18 meters, which is smaller than any particular present model for the electron. And the result is that the electron is presently assumed to be just a point or point-like particle having basically no dimension, but having the properties of intrinsic spin, magnetic moment, charge, and mass. So what I did was to try to relate the photon to the electron in basically a single composite model, where both I described the photon and the electron in terms of a helical movement of momentum. I made a kind of interesting discovery, as I think it is a discovery, when I modeled the photon as a helical movement of momentum. If you model the photon as a helical movement of momentum, then the transverse and longitudinal components of the momentum of that helical motion can be related to the momentum of a photon, which is h over wavelength, and the spin of a photon, which is h bar. If you treat the electron as a helical movement of momentum, and you treat that therefore as a geometry of momentum, then you combine the information of the linear momentum and the angular momentum, then you get a sort of an interesting result as a geometrical solution. And if you assume that one turn of the helix is equal to one wavelength of the photon, then those three sort of points of information
information, when combined, give you a geometry which has a solution that the forward angle of the momentum is 45 degrees, and it's 45 degrees for all wavelengths of photon. This is sort of a geometrical proof which I have. Because of the 45-degree angle of the forward angle of the momentum, it also means that the cylinder describing the helix has a circumference which equals the wavelength of the helix. 45 degrees implies that the circumference equals the wavelength. So the forward angle is 45 degrees, the photon's helix radius, therefore is found to be r equals the wavelength over 2 pi by geometry, and therefore the speed of the momentum flow is greater than the speed of light, and because of 45 degrees, the speed of the momentum flow is the speed of light times the square root of 2, 1.414 times the speed of light, if you model the photon as a momentum flow in a helical direction. So there you have a superluminal internal velocity of the photon. You see, in order to have a spin of the photon, you can't just have forward movement. You have to have sideways movement, and it comes out to be 1.414 times the speed of light. Okay, that's the model for a photon, and the proof of that is in the handout that some of you have, and it's about that long, but basically it's the proof of this 45-degree result, which you can see in the handout. Now, so with that result, I model a photon. Thinking forward that I also want to model the electron, I model the photon as not a point of momentum, but a sheet of electric charge moving forward in a helical path. And a photon, because it's neutral, has a positive and negative sheet of helical charge, both moving together, moving in that 45-degree helix. If you unroll that positive and negative sheet of charge, you get that geometry that I found, 45 degrees. The height of that rhomboid picture is equal to L, the wavelength of the photon, because the radius was L over 2 pi r, so that the height itself, which is the circumference, is equal to L. So if you wrap that up, you get a photon model which is moving forward at the speed of light. Okay. That's the photon model. And now, what is an electron? Thinking the same way, if a photon is an open spiral of a sheet of moving charge, positive and negative, then an electron could be a closed helical movement of sheet of electrical charge. Once David Bohm mentioned that an electron is a photon chasing its tail. The idea being that an electron is a closed structure, but having something like a photon, but moving internally. So I model the electron as a photon which closes on itself, a helix that is closed instead of open. When I do that, the simplest, the structure that corresponds to what I finally solve is this is a closed helix. It doesn't look like a helix because it's closed. It closes on itself, and the helix doesn't close after one turn. In fact, the helix goes around 2 times before it closes. That gives the 720-degree symmetry of an electron going around, like in quantum mechanics, you have to go around 2 times before it closes. This is what the closed helical path of the electron looks like.